we have something called the percent yield, right? And what it is the percent yield is a comparison between how much product you produce in a reaction in terms of grams or moles or whatever it is, and compare that to the theoretical maximum that we now know how to calculate with stoichiometry of the reaction. So how much do you actually produce in real life versus how much could you theoretically produce? And that's going to give us sort of like an efficiency of this process that we have here. So the percent yield is basically going to be the mathematical calculation of the actual yield. So this is how much you actually collect. And then you have that and you divide by something called the theoretical yield. We're going to talk about that in a second. Theoretical yield, right? And then you take that division, this is going to produce a fraction, and to turn that into a percentage, we're going to multiply that by 100, but we do the multiplication later, right? So if you think about it, the theoretical yield always has to be, that's the theoretical maximum. The actual yield is always going to be less than or equal to the theory, right? And so because of that, the top number will always be equal to or smaller than the bottom number, and so this is going to be a fraction. In general, it'll be a fraction less than 1. Some decimal like 0.99 or 0.97, 0.62, something like this. When you multiply by 100, you turn it into a percent. So the best way I can sort of describe the percent yield, it's kind of like an efficiency number for the chemical reaction. You know, when you think about automobiles, electric vehicles, rocket engines, any kind of mechanical device, you always have the theoretical amount of output of whatever it is you're talking about. In terms of a rocket engine, it might be a theoretical thrust. This is the calculation, the calculational theoretical thrust that you get from combining the whatever it is, oxygen, hydrogen, or methane and oxygen, or whatever it is. How much energy is released and focused into a rocket nozzle, how much thrust can you get from that theoretical calculation? But in real life, rocket engines have pumps and motors and bearings and friction and air resistance and all kinds of things going on that basically limit the actual thrust to be something a little bit less than the theoretical thrust. So I'm using a rocket engine, but it could be any kind of machine. Internal combustion engine, an electric motor, pretty much any type of anything, even a solar panel, has a theoretical amount of power output, but the real power output will always be less than that. It can never be greater. It has to be less than or equal to the theoretical maximum because the theoretical maximum is the theoretical maximum, right? So, what is theoretical yield? In terms of chemistry, I could write this definition down, but this number on the bottom, this theoretical yield, is we're talking in chemistry about taking reactants, reacting them together, and then they make products, one or more products on the right-hand side of the yield arrow in a chemical reaction. So when you have a given amount of reactants, the theoretical yield is the number that we calculate using stoichiometry. Remember, we often have to find the limiting reactant. Which of these reactants will run out first? Whichever one runs out first is going to stop or limit the chemical reaction, and that is going to govern how much product is produced. So when we did our limiting reactant problems, we figure out which is going to run out first, and we calculate the amount of product made in that situation once the limiting reactant is exhausted. That's called the theoretical yield, because you know which one's going to run out first. You run it through the stoichiometry of the reaction and figure out how many moles or how many grams you're going to make on the right-hand side of the reaction. But that is a theoretical maximum, right? Now in the real world, things are not perfect. In the real world, large chemical reactions are not done in a test tube this big. They're done in a gigantic reaction vessel, right? Which may have many tons of material inside. You need to stir agitate the reactants to get the atoms to actually touch each other and have the chemical reaction. But if the reaction vessel is too large and you don't have very good mixing of the reactants, then maybe you don't get all of the reactants to react because maybe the mixing isn't so good. If you build your reactor vessel to not have good mixing, then you're not going to have the theoretical maximum. In the rocket engine, you need very good mixing of the propellant and the oxidizer to mix together very, very, very good in order to get complete combustion. And if they don't mix that great, then your actual thrust will be less than the theoretical thrust. Same thing in a chemical reaction. What other problems can you have? You could have something called side reactions. So you're mixing these things together to get them to produce what you want them to produce, but sometimes you have other reactions, side reactions taking place that are not as common or not as prevalent as the main reaction, but they can lower the amount of yield that you have, lower the amount of product that you get, because maybe, you know, some hydrogen and some oxygen come together and make some water instead of whatever it is you're actually trying to make. And you try to design your reaction process to limit the amount of side reactions so that you can get as much product as you can. That's the whole idea of designing chemical reaction vessels, right? And then, of course, the other issue is that once you make the product, you see, we just write a reaction on the board, right? This plus this yields this plus this, and it's just on the board. But in real life, you have to mix these things together, and then they react. But the product of the reaction is in the same reaction vessel as the reactants. And you have to figure out how to remove the product. What if the product is a solid and it settles to the bottom? How do you get it out of there? What if you're not able to get it all out of there? In other words, you might produce a lot of product, but if you can't separate it from the rest of the materials being reacted, then you can't get the theoretical yield because you can't take it out. What if your product, instead of being a solid, is a thick, syrupy substance, and the reactants are just something on the order of water, something that's not so thick and syrupy? How do you take the thick and syrupy stuff out of there and allow the remaining stuff to continue reacting? So in a theoretical world, we just write the reaction down and we say it's going to happen. But in the real world, when the product starts to be made, if the product starts interfering with the original reaction, then you're going to start limiting your reaction from taking place. You have to remove the product. If you can't remove the product in an efficient way, then you're not going to get your theoretical yield. So your actual yield, this top number, is always going to be less than, in real life, your theoretical yield. You could theoretically get 100% yield if your actual yield was equal to the theoretical yield, because you would divide these, you would get the number 1 times 100, and that would give you 100% yield. But in real life, you never get 100% yield of anything. I mean, you may get close, but you're never going to get really 100%. So that's the idea between percent yield. I want you to think of it as an efficiency metric for the chemical reaction. How close to the theoretical maximum are you actually able to collect in terms of the product of the reaction? All right, now we're ready to solve our first problem. The problem says, below, I'll write it on the board, is the reaction between benzene when it reacts with bromine to form bromobenzene and hydrobromic acid. Now, if you don't know what benzene is, it's okay. We haven't covered benzene. This is not an organic chemistry class. But benzene is a very common chemical that we study in organic chemistry. It has lots of industrial uses, right? Reacts with bromine to produce hydrobromic acid and bromobenzene. So C6H6 plus Br2, that's the bromine, is C6H5Br plus HBr. The HBr is the hydrobromic acid. So 2 parts. First part is, what is the theoretical yield of bromobenzene if 30.0 grams of benzene reacts with 65.0 grams of bromine? So when a question asks you, what is the theoretical yield, then you need to translate in your mind. When someone says, what's the theoretical yield? It means you must find the limiting reactant, figure out which one's going to run out first. From that, you use the stoichiometry to calculate the amount of product you're going to get. That is what the theoretical yield is. But the first step is you have to figure out which of these two are going to run out first. Is it the 30 grams of benzene that's going to run out first, or is it the 65 grams of bromine that's going to run out first? You have to figure that out in order to figure out what the limiting reactant is. All right, so let's start our calculation. All right, we are given, I'm going to write this down, I think, underneath here. I'm going to write down the reaction. The reaction is C6H6 plus bromine, Br2, that's a diatomic molecule, yields C6H5Br, that's the bromobenzene, and then plus hydrobromic acid. Now, first thing we always need to do is determine, is this balanced? 6 carbons, 6 carbons, 6 hydrogens. Here's 5, one more is 6 hydrogens. 2 bromines, there's 1, there's another, 2 bromines. So this is actually already balanced. Every molar coefficient is just a 1, but it's already balanced, that's okay. Now what we're doing in this problem is we are going to react exactly 30 grams of benzene, C6H6, and we're going to react with that 65 grams of bromine. So these are the two reactants. I'm telling you, in a reaction vessel, I'm going to have this much of the benzene right here and this many grams of the bromine. Now, you don't know ahead of time which one's going to actually be exhausted first. That's what we have to find out. So let's start that calculation to figure out which of these two will be the limiting reactant. Let's start with the 30 grams of benzene. Let's write down 30.00 grams of benzene, C6H6. All right, so we need to figure this out. Now, as we learned before, there are multiple ways to figure out what the limiting reactant is. But ultimately, since I'm going to be calculating the percent yield, or the theoretical yield, and later on the percent yield, haven't gotten to part B yet, but that's what we're going to do, then we really want to figure out how much product is forming. So yes, I know that I could figure out the limiting reactant by seeing how much bromine this requires and then figuring out which one's less, or which one is going to be exhausted first. But actually what I want to do is calculate, based on the benzene I have, how much bromobenzene can I make, and then I'll do it again starting with this. So basically, if I convert this 100% to product, how much do I get? If I start with this, how much product do I get? And just see which of the products is less, because that's the other way to calculate a limiting reactant. So we start with both of our reactants, convert each of them fully to product, see which one yields the least amount of moles of product. All right? So we have 30 grams of benzene. In order to use the reaction, I have to go to moles, and I have grams. So we're going to go to the other board, and we're going to figure out what the molar mass of benzene is. So we have C6H6. That's 6, and then carbon is 12.011. I happen to remember that. And then 6 of hydrogen, I remember that one too, 1.008. And so if I take 6 times this and 6 times this and then add those numbers together, I get 78.114 grams per mole. 78.114. So I'm going to go here and say 78.114 grams of C6H6 is exactly equal to 1 mole of C6H6. Now this cancels with this. So if I stop the calculation here, I am now left with the number of moles of benzene that I start with. Now I want to calculate if I could convert all of the benzene I start with into product, this being the product I'm interested in. How do I do it? Well, in this case, there's 1 mole of benzene yields 1 mole of product. So since I have benzene on top, I say 1 mole of C6H6 yields 1 mole of the product, C6H5Br. All right, cancel, cancel. And so what units do I have left? I have moles of the bromobenzene over there at the end. So if I take 30 and then times 1 divided by 78.114 times 1 divided by 1, I get 0.3841 moles of C6H5Br, bromobenzene, of product. Now, I have to do the exact same thing. That was basically this is basically what is happening if I start with 30 grams of this reactant and react it with an excess amount of benzene. In other words, give me bromine, tons of bromine so that it can fully react. How much theoretical product would I produce? This is how much of it I produce in that case. Now, we're going to do the other thing. We're going to start with 65 grams of bromine and react it in an excess of benzene. So give me tons of benzene, convert all of this bromine to product and see how much that I would get in that situation. So it would be 65.00 grams of bromine, Br2. Now, what I have to do in order to do the stoichiometry is I need to figure out the molar mass of the bromine molecule, because bromine's a diatomic molecule. So I'm going to go off to the side because I have to get up to moles there. And I'm going to take a look at Br2. And you can, of course, look at the periodic table. Periodic table has bromine at 79.90 grams per mole, because I don't remember that one really. And there's 2 of them. So it's going to be 2 times 79 point, I'm going to use 904 grams per mole. And when you multiply that out, you get 159.808 grams per mole. 159.908 grams per mole. Now, I'm going to write this here, 159.908 grams of bromine is 1 mole of bromine, Br2. Okay, grams cancel with grams. So if I stop the calculation, now I have the moles of bromine that I start with. Right? Now, if I look at the stoichiometry, it's 1 mole of bromine gives me 1 mole of product. So I'm going to put that here. 1 mole of bromine gives me 1 mole of the product, C6H5, and then Br. Cancel, cancel. And essentially, I'm done here. So what I'm going to do then is I'm going to multiply. So 65 times 1 divided by 159.808 times 1 divided by 1 gives me a yield of 0.4067. This is moles of C6H5Br. So this is all in the effort of figuring out what the limiting reactant is. Which one's going to run out first? If I take this reactant and convert it completely to product, I can make this much product. If I start with this reactant and convert it completely to product, I can make this much product. What situation is really going to happen? This situation is really going to happen. I cannot make the 0.4067 moles of the product because since I'm mixing this amount together, what's actually going to happen is this reactant, the benzene, is going to run out first. So I will make this much product and then the thing stops because I've run out of reactant. I've run out of the benzene there. So the limiting reactant is the benzene in this case. Now, part 1 says, what is the theoretical yield of bromobenzene? Now, it doesn't ever say what is the limiting reactant, but we now know that the limiting reactant is the benzene. So I'm going to write this down. So the benzene, the C6H6, this is the limiting reactant. So I don't want to scratch this out because I needed to do it to figure it out, but ultimately this whole bit of math doesn't do anything anymore. I know that this didn't happen. This is what actually happens when I do this reaction. And so what's really going to happen is I'm going to form 0.3841 moles of the product. So I'm going to start now with saying 0.3841 moles of the product being the bromobenzene, C6H5Br. All right, that's how many moles of product I formed. Now, the actual question says, what is the theoretical yield of bromobenzene? I now know how many moles of bromobenzene is formed. Now, it's perfectly fine for me to say that the yield in this situation is 0.3841 moles, because that is a representation of the amount. But I want to go ahead and convert it to grams, and the reason is because part B, which we haven't gotten to, it tells me the theoretical, the actual yield in grams, and then we have to calculate the percent yield. So I know I'm going to need to have it in grams in order to do part B, which we haven't really gotten to yet. So you can stop here and say, well, this is the actual or the theoretical yield, but let's go ahead and convert it to grams. So I need the molar mass of bromobenzene to go from moles to grams. So I'm going to go up here, and I'm going to say, what's the molar mass of C6H5Br? All right. And so in that case, I know that there's going to be 6 carbons, which is each is 12.011 grams per mole. And there's 5 hydrogens, 1.008 grams per mole. And then the bromine, there's only one of those, and I looked that up before, it's 79.904 grams per mole. So if I take the 5 times the hydrogen and the 6 times the carbon, and I add all it up with the 1 bromine atom there, I'm going to get 157.010 grams per mole. This is the molar mass of the bromobenzene, 157.010. So I know that then 1 mole of the bromobenzene, C6H5Br, is, what did I write down? 157.010. This is grams of C6H5Br. Cancel, cancel. Okay, so then I can put an equal sign here. And if I take 0.3841 and multiply by 157.010, of course, divide by 1, that doesn't do anything, I'm going to get 60.31 grams of the bromobenzene, C6H5Br. So part A, or the whole problem up to this point, says, hey, here's a reaction between benzene and bromine to form bromobenzene and hydrobromic acid. What is the theoretical yield of bromobenzene if 30 grams of benzene reacts with 65 grams of bromine? So we write down the reactants and we have to find the limiting reactant. And we figure out that since, in this case, less product forms, then this case, when the benzene here must run out first, it's the limiting reactant. This is how many moles of the product bromobenzene is formed. We just convert that to grams, and we say that 60.31 grams of the bromobenzene will actually form. Now, part B says, what is the percentage yield if the actual yield of the reaction is 42.30 grams of bromobenzene. So what we're saying is we've calculated in theory what will happen. Now we're saying we actually do this in a lab, but we actually are only able to collect 42.30 grams of this bromobenzene. What is the percent yield? So we'll say the percent yield. The percent yield is just going to be the actual, whatever you actually collect, divided by the theoretical times 100. The actual yield is 42.30, and that's in grams. And then the theoretical yield is 60.31, and that's also in grams. 60.31, right? And that's in grams. And I'm going to multiply the result times 100. So what I'm going to get when I divide these, the units cancel. So this is a dimensionless number, 42.31 divided by 42.31 or 30 divided by 60.31 is going to give you 0.7014. This is the decimal that you get when you divide by those, smaller divided by bigger. Got to multiply by 100, and so what you get is 70.14%. So this is a percent yield of 70.14%. So if you're working in a chemical lab somewhere, or a chemical plant, or producing some sort of industrial product of any kind, and someone comes to you and says, we have some reaction process, and our percent yield is 70.14%. You know in your mind that what that means is they're collecting 70 parts out of 100 in terms of the theoretical amount that you could calculate now, or that you could capture. So the question remains, if given these input amount of reactants, and I'm calculating that this is how many moles of product I'm making, which corresponds to this many grams of product I'm making, 60.31, why am I only able to collect 42.3 grams of it? And if you can collect any more product, then you're going to increase this percent yield closer and closer and closer, so that eventually, if the actual could ever equal the theoretical, then you would just have a 1 here, and you would have 100% yield. That's never going to happen. But how do you get closer? Well, you look at things like, how is the reaction vessel designed? How are you, once you see you're combining these together and you're making two products, hydrobromic acid along with this. How can I remove this bromobenzene properly without accidentally screwing up other stuff? Like if I'm removing this from the reaction vessel, but I accidentally remove some benzene along with it, then I'm going to stop the reaction even earlier, because benzene was already the limiting reactant. So let me say that again. If I start removing this, you know, because remember, in a reaction vessel, it's just liquids in there, right? They're not labeled with labels saying, here's the bromobenzene, here's the regular benzene. I mean, you have to remove it somehow. Is there a centrifuge involved? Is there some sort of filter system involved? All of that stuff is engineering, right? But in the course of removing this from the reaction vessel to figure out how much you have, if you accidentally remove a little more benzene with it, then you don't have 30 grams initially anymore. You have less because you're removing reactant with it. And that's a great way to slow down a reaction if you accidentally take some reactant out of the vessel. That's one example. There are many, many others. But the idea is to talk through it to understand why we have a percent yield calculation to begin with. If someone tells me I have a 70% yield, I'm going to try really hard to get that up to 75 or 80 or 85 or 90%. But if somebody comes to me and says, we've got a 99.2% yield, I'm probably not going to worry about it too much, because it's going to be unlikely I'm going to get that much closer to 100%. It depends on what you're doing, but that would be my first reaction, okay? Now, I'd like you to solve this yourself. We're going to work a few more percent yield problems, so follow me on into the next section, and we'll continue the process of solving percent yield problems. Learn anything at mathandscience.com.